So I will start with an introduction to debugging and parallel debugging. And then the second part is running the Linearo DDT parallel debugger. So the traditional way of debugging is commonly referred to as printf debugging. Printf is C, but I have here that in many contexts, in Fortran, in Python, whatever. So if you do printf debugging, you add extra print statements to the code, and that indicates whether the code has reached a certain stage, and you can print key values at that stage. There are a lot of issues with that approach. You need to modify the source code and recompile, and it's an iterative approach and requires frequent recompiles. So quite often, sometimes you have it, you start with a debugging project, something is wrong with your code and you have no real idea where it happens. You might put a few print statements scattered over the code. After a quarter of the runtime, half the runtime, 3/4 of the runtime, and then you compile and run in the hope that you get some information where the problem comes. Then you have it down to roughly a quarter of your code. So if you know in which quarter of the code the problem sits, then you put in print statements in that quarter and go on and on and on and on. So finally, you might have solved your problem, and then you're left with a completely destroyed source code because it's full of print statements. And debuggers are more convenient here. They allow working with unmodified source code. You typically step through the code, executing line by line, or run a small section until you get to the troubled part. And then you can just look what changes if you run through the code line by line. You can look at variables and explore an area where there's a problem in a more reactive way. On Linux systems, they typically come with GDB as a debugger, and that is a command line execution interface. There are GUIs for that, and I would recommend using a GUI instead of command line execution. And access to GDB is often integrated into development platforms. If we go into parallel debugging, things get a bit more complex or even more complex. Can you not hear test. So it seems that some people have audio issues. Yeah. So I can hear somebody typing. It's a bit tricky. If I ask here those to raise their hand which have audio issues, those will not hear it.
Maybe you can write it in the chat. So
I tried it. I tried. Does anyone get the audio? Okay, somebody wrote, Peter wrote that they can hear. It seems audio issues. At the end of the participants not hearing. Okay. So before starting, try to simplify the task. Reduce the problem size that holds for any type of debugging. There is no joy in debugging a problem which has matrix sizes of 1,000,000 and something is wrong there. Check whether the problem exists. If you reduce the problem size, it is still there. The smaller the problem size, the smaller the data structures, the easier it is to find. So there's a lot of point to be said with respect to reduce the problem size before you start. Then with parallel, is the problem still there if you reduce the task or thread count? If you have hundreds or thousands of computational tasks or computational threads, debugging is very, very difficult. If the problem still exists on something like 4 or 10 tasks or threads, your life is a lot easier. Printf debugging is even more problematic than in serial. So if you just write print statements, your output gets totally littered. You have no clue who wrote that. So when I have to resort to printf debugging, so for instance, no access to a debugger, I typically write in the beginning a small thing about the task ID or the thread ID, such that I can use tools like grep to give me the output from thread 1, to give me the output from task 2, or something like that, such that I can filter that. If you have 10 computational entities, tasks, or threads writing, it's very, very convoluted. If you resort for printf, I strongly recommend writing in the identification of the task thread in the beginning of the line when printing, and do it in such a way that you can reliably grep for instance, task 0, and that doesn't get confused with task number 10. Parallel debuggers, they exist, but licenses are very expensive. With the NACE, we are lucky that we currently have a license for all of the NACE machine. And I often think if you're a code developer, just the access to the parallel debugger is worth a lot. So on the other hand, if you don't have access, I still believe being able to do some printf debugging is an essential skill. If you sit on a machine, there's a problem. Writing something instead of starting the machine is an essential skill. If you develop on a NACE machine, actually, I would not touch printf debugging anymore. That is the second point, that parallel debuggers became more usable over the years. I have been using this type of programs for something like 20 years. In the beginning, the integration with something like a job scheduler was utterly poor, and one had to jump through a lot of hoops to get that working inside the job scheduler environment. And so I've typically first tried to sort myself with printf and only started the debugger once I couldn't get anywhere with printf anymore. It was too complex or of that kind. These days, if I develop on a NACE system, or if I have the code on a NACE system, I do not go into printf debugging at all. If there's a problem, I just start the parallel debugger and start it over there. I will show you that in a minute. So the usability has dramatically improved, and it is not, I would just go directly there. I'm aware of two products in this area. One is TotalView for HPC. I give the URL here. I haven't used that product in 15 years, so I only mention that it exists. I'm not qualified to give you anything, whether it's better than DDT or inferior than DDT, whether it works well or whatever. I would not like to comment, since it's 15 years ago that I have used the product, and 15 years is a lot. You would expect that they made a lot of progress. As I said, with the NICE, we have access to Linearo DDT, which is part of Linearo Forge. So Linear Forge is a package of two applications. There's the DDT debugger and the map performance profiler, but today we are only covering the DDT part. That product was formerly known as Alenia DDT or Alenia Forge, and then ARM DDT and ARM Forge. So quite often, if you speak to people, you might hear people speaking about Alenia DDT or people speaking about ARM DDT, and others speak about Linearo DDT. It is all the same product. So in the field of high performance computing, these old names of Alenia DDT and ARM DDT do not have not really died out. The other thing is, if you start working with the product, you see that a lot of environment variables, a lot of settings are still named Alinea. So to some extent, they also didn't clean up their act with respect to marketing. So this is quite important for you to remember that that Alinea DDT and ARM DDT and Linearo DDT refer to the same product. Okay, I want to go into preparations and starting DDT. As I said, this has become a lot easier. So in general, on an A system, I would look for a VNC solution like the Synlink, which we employ in NACE, and a lot of centers employ them. So what you need to get a DDT working, you need access to the GUI. It's no joy at a command line, and so I would look at a VNC solution. If that fails, you might want to try something like X forwarding. But for my own work, I typically do not bother with X forwarding. I go for the VNC solutions like Synlink on Tetralead and do my debugging there. You have to rebuild your application. So the recommendation, one thing is the -G flag. What that does is that it links the instructions to the source line. If you don't do that, the executable has no connection to the source, and you have to look into assembler, and that is typically, if you're C or Fortran or Python programmer, that is not what you want. So if you're working with C or Fortran sources or C++ sources, please give the -G. Then the next is a recommendation to switch out all optimization by putting a flag of -O, capital O 0. That you can run with optimization, but then with optimization, the compiler restructures the code. Certain things vanish from the source. Some variables, the compiler might just optimize that out. It might reorder statements. So if you optimize, the link between a source statement and the instructions is weak. So if you then step through the source in the debugger and have optimized, it happens quite often that what the line highlighted in the GUI is sort of one, two, three lines before or above where it is actually executed. So it's a bit a double-edged sword. So the lack of optimization slows code. In particular, if you're working with C++ applications, they often only get decent performance if you start inlining, if you start optimizing, and so the code performance can be slow. The other thing is if you remove optimization, I have seen that often that the problem might disappear without optimization. So that is because the code gets reordered, and for instance, if you overrun a data structure such as an array, the data structures might be organized in a different fashion than they were organized beforehand. And if you overrun an array beforehand, you might have destroyed something important. And now, without optimization, you are not destroying something important anymore, and the bug appears to be disappearing. I actually had that happen also with printf debugging. putting in a few print statements in the troubled area, and everything changes, and suddenly the problem has gone away. Very hard to debug, but that's life. So if you face that problem, please have a careful look at your data structures. You might be overrunning a data structure. As I said, you can optimize, but then it's tough to match code line to instructions, and that might not work. So you have to be a bit flexible with the output from the tool. If you do it with optimization, that what is highlighted is not what's actually executed. If the problem appears under optimization and disappears if you switch optimization off, I would always try to have a go and see whether I can make any sense of the output or not. So in general, don't start debugging on the front-end node. If you run in particular with parallel codes, you occupy a number of cores. And if you didn't succeed very well with cutting down your memory, you're eating a lot of memory, and you might make life miserable for everyone else using our systems. So in NACE, typically you have to use the backend, and there are two ways. There's using an interactive session and using a Slurm script. In my own experience, using an interactive session is way more delicate than using a Slurm script. Using an interactive session is on the other hand a bit more convenient, but I will show a trick that when using a Slurm script, you get almost a similar level of comfort as using the interactive session. So oops, there are messages in the chat. Oh, it's still to the there's a question about open source MPI debugger tools. I'm not aware of any. Let's phrase it that way. You never know whether there's a project in some corner, but I'm not aware of anything existing.
Thank you.
Yeah, Valgrind, it's a different product. It does some similar things like DDT can do, and okay. So using an interactive session, I stated it is more delicate than using a Slurm script. So for instance, when preparing the seminar, I did not succeed getting Python debugging in the interactive session. Within the time I could afford to try to get it going. But I managed to get that going in a non-interactive session. I didn't get GCC 13 to work in an interactive session. I got a GCC 13 working in a Slurm script. So, but in general, that is perhaps a comment. In my experience, DDT is quite delicate. So if I go back to a debugging project a year after I have used that before, there's a new compiler, there's a new OpenMPI library, and I quite often discover that it does not work. So the first thing I have to do is to install a new version of DDT, and then it typically works. So sometimes, if you use a new compiler, if you use a new MPI library and it doesn't quite work and the problem is not exposed in older versions, try contacting NACE support and see whether they can install you a newer version. This seems to be a cat and mouse thing. As I said, interactive session, when it works, it is more convenient. So you spend less time waiting for job to start. But as I said, depends on what you're doing, how you're working. This might be a non-issue. So to start an interactive session on TetraLead, you write interactive. So here I ask for 6 cores, 60 minutes. So something like an hour or two for a debugging session doesn't seem excessive. And then depending on your account, you might have to give an account that it runs. Then so one comment here I want to make is the interactive session. Essentially what it does in the background, it writes a Slurm script and you just queue. If you here write 1000 cores, you will queue like for a 1000 core job. So don't expect that to open anytime soon. If you have succeeded, if the problem exists on 6 cores or 4 cores, ask for 6 cores, ask for 4 cores, and your life in debugging will be easier, and you get your interactive session will become live quicker. Once you're there, you load the modules. So for the demonstrations, I have built environment GCC 2022A EB that works, and then you have to load the debugger. So on as you see on TetraLead, they are still called ARM despite being the Linearo product. And then you might need to compile. So I have just sketched that out for a simple application. So you might have to go into your make procedure that or everything gets compiled with -G and -O0. And then you can start the debugger with DDT. On TetraLead, the recommendation is to specify which MPI library you're using. So I have tested things with OpenMPI, so I specify to DDT, please use OpenMPI as the MPI library. DDT supports a number of MPI libraries. It supports the Intel libraries, it supports MPICH, but for my own work, I typically use OpenMPI. Then you give the number of cores. You can get that from the environment variable slurm and procs, and then you put your executable. The DDT GUI will start and ask you a couple of questions, which we will discuss later. So the next thing is I would like to discuss how to start the GUI on TetraLead in a job script. So you start the GUI on the login node and keep it running. So this is a small lightweight GUI. It shouldn't affect anyone else. So on the front end, module load arm DDT, and then you can put DDT and ampersand such that you get control back, and then the GUI will open if you're on top of your X forwarding. So for instance, using the Synlink clients. There's a remote client for your desktop. And you can connect to the front end of an HPC service. I had used that 6 years ago. That was on a machine where the Synlink wasn't really installed. On modern NAS machines, I typically do not bother. So as I said, I'm sitting in Lund right now, and I have worked the past days on TetraLead in Linköping, and using Synlink, it works all quite nice and well. So let's hope that that continues when we do the demonstrations. So if you start DDT, you get a window like that. It says Linearo Forge because it supports both application. And here it's the Linearo DDT is highlighted since we started at it on with the DDT command. That window opens and the recommendation is just to leave it alone. Then you go into your job script. So here are general modifications. So you need to modify your job script. Make sure the relevant modules are loaded, compiler, MPI libraries, other libraries, and Linearo DDT or Linearo Forge. And then you prefix, so if you normally run like MPI run MPI hello, the standard recommendation is to use DDT dash dash connect, and this dash dash connect, that is the magic. That was introduced something like 10, 13, 15 years ago, and that to me made a huge difference. So what that will do is that you put that in a job script. This DDT command will run on the compute node, and with the connect, it will make the connection to the GUI which you have just started on the front end. It's all very magically, and typically that works very well. It has not failed me, and that is what makes the thing shine, makes the things convenient. So if you have a simple job script, just write DDT connect in front of it, and keep the rest as before. If you have a complex scripting setup which starts your application, you have to hack into that, or see whether there's already support for a debugger, and to get that before the job launch. If you have a Python, normally the recommendation is to start a Python by MPI run, Python 3, and then the name of your Python script. You have to put that string here in the middle. You see it's still named alinea. And you prefix DDT minus connect. So it's marginally less convenient than for C and Fortran, but it's not a big deal. You just have to remember, you just have to remember to put that thing here. With Tetralead, the recommendations are a bit different. It is a setup. NSC provides setup which is typically quite convenient, but then you have to get DDT to work around that. So as a launcher, I would recommend DDT dash dash connect minus MPI open MPI, and the setup supports that you just give the executable directly. It's not required to use MPI run. In my tests, giving MPI run doesn't harm. And if you go into Python 3, if you want to debug Python, I had this one here. This seems to have worked for me. Dash dash connect. Here, whoops, there is a typo. Things try to be clever. Too clever for their own good. Now, come on. Connect as again specifies that you're using OpenMPI if the MPI for Pi in this setup is built against OpenMPI. If it's built against a different MPI library, you have to specify what it's actually using. And again, here you have to put that string in the middle, and then you give the name of your Python script. And then you just submit the job script as before. And as I said, once your job starts running, by magic, a reverse connect request appears in the GUI which you have started on the front end. And when that comes, you just hit accept, and you get placed into session. Then you get asked a few questions. And in the beginning, I just hit run here. And then after some jiggly pokery, you end up with such a window. Here in the middle, you have your source. If you have the -g, if no source is there, then you most likely forgot that there's a -g. Here you have your files and the methods inside. You have your variables, and here you have various other things, some of which I discuss. And above here, that is quite important. So this is an MPI code running on 4 MPI tasks. And here you can switch between the 4 processes. So currently it's showing the state for rank number 0. As I said, it starts one line after MPI init. So if you debug MPI code, if you have executable statements before MPI init, you will not be able to debug that. So in my experience, when debugging, frequently starting over is required. So with the debugger, stepping backwards is typically not possible. So if you have a problem in a code and went are through 3 lines past the problem and you want to go over the problematic section again, typically you have to restart. So very important or very useful is if you want to start over, if you're running out of a job script, go here, File, Restart Session, and then your job script will not be terminated. Your job script keeps running and DDT will start your code again. Just a quick reminder if you have an understanding of how stuff works. So in principle, if I start like, perhaps I should just start this one. So here my executable is DDT, and that is what I'm running in the job script. And then you tell DDT, please use the job launcher MPI run, and the executable is this. But as far as Unix is concerned, in first place, DDT is the process which runs. It starts the process MPI run, and MPI run in turn starts MPI hello. So by using this feature here, you just tell DDT, please issue terminate the one MPI run and start a new MPI run. And then MPI run doesn't understand that it lives inside DDT. It just continues. So this is very, very important if you have to work out of a job script, if you're not in an interactive session, because then you don't need to queue again. So as a remark, also in a job script, when using DDT, I give quite a long time, 1 hour, 2 hours, for how long I expect my session to be, that I can debug and frequently do restarts. With Python, things can be a bit tricky when starting. It might want to start all sort of things, might want to debug all sort of things which are not really interested. So the first thing is that in the stack window, which is here, you have to locate your Python script and place that on this. And then the recommendation is to set a breakpoint or use a run to here for the first line after importing MPI for Pi or importing from MPI for Pi. This is, as I said beforehand, the MPI, the debugger starts one line after MPI init, and how MPI for Pi is crafted, you are issuing MPI init when you import the thing. So if you don't do that, setting a breakpoint after the first on the first line or using a run to here for the first reasonably line after importing MPI for Pi, you start debugging the import process, which you typically would not want. Okay, okay, let's take some questions. Anyone a question? Any comments? No? Then I would like to do some demonstrations. That you get a bit more of a feeling for it. So I need to. So this is my Synlink session to Tetralit. So that runs over 300 kilometers from Lund to Linköping. So let's start with loading a module. So I'm now on GCC 11 and I load the debugger. My recommendation is to load the latest and most modern version installed on the system. And when we want to do Python, I need an MPI for Py. If we just have a look, we see I have quite a number of modules. I said I start now off by starting the GUI, and I get a GUI on my window. I need to compile. With OpenMPI, it's MPI F90 for Fortran F9. That's the old fashioned. The new one is this one. Yeah. So here we have a batch script. As I said, take a decent amount of time. Let's do on 4 cores. This is all the standard. Then here, this is one of my personal favorites. This line, cut $0, puts the Slurm script into the job output. So if things don't work, I can always see what I had in the Slurm script. I make sure that the debugger is loaded. The recommendation in Linshapping on Tetralead is not to use to load the build environment inside the Slurm script, so I have taken that out. On other machines, it is the explicit recommendation, so please check the documentation of the system you're using, what is required. And here we have DDT --connect. I specify the OpenMPI library, and I give the name of the executable, which I have just compiled. So let's save this. And we just submit the batch script in the fashion which we have done before. And now, if I were to use an interactive environment, I would also use this time here. So here, it isn't that magic, isn't that magic? So we are running on compute node 958, and compute node 958 now connects to the front end where the GUI is running. And do you want to accept the request? We hit accept, and it makes connection. We specified 4 processors, so I changed that here. So it lists here the application. It has it here, so in principle you could edit that. Since this is pure MPI, it has 4 processors, open MPI, and we can just hit run, and now comes we are placed in session. Isn't that magic? I said that before, we start in the line after MPI init. Here I can see all the cores, not much has run. These things are 0. I can show, if I go current line, it shows me the variables on the current line. If I go to locals, I can see all variables. So for instance, here name is all over the place. I can, this focus is quite important. You have group, you have process and thread. So since this is a pure MPI example, threads, you will see threads popping up. I assume that is how OpenMPI manages to do its business. So it starts threads inside the MPI library. But for pure MPI code, group and process is what is important. So we can, if we focus on group, if we hit that line, we make one step. You see we have moved one line, and you see world size is 4. I can go, if I change the process, it shows me the value of world size for all the cores. Do another one. I don't know why it does that. It jumps away and then it has done all of these things. Older versions, they just went line 18, line 19, line 20. This version here with this version of OpenMPI behaves like that. So what I would like to show here is, for instance, world rank. If you have world rank, so I have just queried the rank, and on rank 0, it should be 0, it is 0. On rank 1, it should be 1, it is 1. On rank 2, it is a 2, and rank 3, it's a 3. Then I like to draw this thing here to your attention. This is sort of like a small graph or histogram, and it shows that on rank 0 you have a low value, on rank 3 you have a high value. So quite often, in particular if you have many ranks, it shows you if that is something which is unexpected. So if I know the code, if I know that world rank comes out of MPI rank, I expect to see this pattern and I can see it directly that it fits. World size, it should be a 4 everywhere, and you see it's a flat line. We have no outlier. So here we have a print statement. If I keep stepping, you see what has happened. Rank 3 has decided that it is not rank 0, and it jumped that if block. Rank 2 jumped, rank 1 jumped, and rank 0 went into it. I can step, and if I just look here I get the output written by rank number 0. You now see that rank 0 is red, that is in a stopped state, whereas if I just go here, these guys are playing in the MPI barrier. They entered the barrier and are waiting for rank 0 to arrive. If I do another one, everyone steps out. Hit another one, and we get all the output. In the typical way, everyone tries to write as fast as possible, and you get something like a real random number generator here. So now we have reached the end. If I step one more, it goes out. And then finally I get that every process in your program has terminated. Would you like to restart the session from the beginning? If I now hit yes, it starts over, starting 4 processes, and I start over where I was in the beginning. So this is so if you reach the end, if you follow, if you want to start over, you can just do it. And my process is still running in Slurm. So despite me using a batch shot, I have more than one shot at DDT. Here are a few more things I can set, for instance, barriers. Breakpoints. If I go on this, do a right click, add breakpoint for all. Then I can, for instance, use this one. This is like a play button of an old-fashioned CD player. And if you just run here, we get process 0 to 3 have stopped, and everyone is in this barrier. I can delete the breakpoint. I haven't shown here process. If I go to process, I can now, for instance, go to 1. And process 1 has entered the barrier. So if I go on process, I can step individual tasks and leave the other ones alone. I can have this guy go into the barrier. I can have this guy go into the barrier. And I can have this guy go into the barrier, and then they're out. And then if I just step this guy, I have written from rank 1. If I continue, this guy is, I think he's stuck in finalized and waits for the rest of the gang to arrive. I can take this guy, and you see that rank 3 has done. I can do back on group, and for instance, just run everything to the end. I have removed my breakpoint. I can it doesn't offer me now to restart. So file, restart session. Very important here, clicking restart session. If you end the session, you end the DDT running on the back end and your Slurm script finishes. So hit restart session. It asks me, I hit yes. Then I can start over. I wanted to show another feature. It's a run to here. So for instance, I can take this line here, right click on this line, and here's a run to here option. If I press that, everyone has run here, so no need to set a breakpoint. It depends a bit how you want to do it. Any questions? Somebody wrote a chat. Yeah, essentially, yeah. The startup is slightly different. It's somebody who asked about Cosmos here in Lund University. Yeah, it's the basics are the same. The basics are the same. The startup is more or less the same. You just put what I had on if you run on Cosmos set applies. Okay, now I would like to do a different code, so I hit end session. And it should stop. So sometimes this just hangs. If you want to a new session to connect here, move that to off. The job has finished. I have here a different code. Let's change that to 4. And here's a magic line DDT connect, open MPI, and set the executable. I think we go for C. Yeah. So I just esbatched this. I had compiled that before. So that is compiled with -G and -O0. I accept and get placed into session. So this is a modularized code. If you just have a look, there's a main method. There's no MPI in it. Here's a setup routine for MPI. So the code has started in here in MPI com. A line after MPI in it inside the setup routine. Can just step. And we get out of here. Then we have this like a hello world. And everyone has written their rang number. So what the code does, it places the MPI tasks on a ring and everyone exchanges data with their neighbors. So it determines here an up neighbor and a down neighbor in a modular type fashion. Let's just see. If I go here, up neighbor on 0, it is 1. On 1, it is 2. It is 3. And on 3, up neighbor is 0. Down neighbor is not set. If I just keep stepping, down neighbor is this one. You can see directly with the histograms, the up neighbor is sort of my rank number +1 unless I reach the end, and it jumps down here. The down neighbor is my rank -1, and if I'm on 0, it is the last one. It's a periodic structure. I step through the code. And then here I have a method exchange, which is declared above. And if I step over, if I hit this, I step over. I do not debug exchange, it's just executed. And it has done the trick. If I want to debug exchange, I go here and I use this one, which is step inside. And then here is some MPI gymnastics to do that thing. And now we are finished, and everyone essentially writes the sum of the rank numbers. So what that de facto is, it's an homegrown implementation of a reduction operation. So here so what I've shown are these things here: step over, step in, and I haven't shown step out. So let's just do that. Restart session. Yes. I can, for instance, use that directly. Step out. The setup has finished, but the ranks and size are set up. So it executes it without you showing it. So if you know that the setup routine is fine, you might just want to step out and get here. Alternative, if we just restart again, I can just scroll in the source. Assuming the problem sits in Exchange, I can just go to that line and run to here. I can do the iterations. I can also put, for instance, a run to here on this one. And then all the tasks are in here. Alternative to a run to here is a breakpoint. So let's set a breakpoint to here. Restart the session. Yes. Yeet. I get placed into session. Here you can hit the various methods inside the file ring send. So it has done here a Fortran routines. And it can do those for you. Jobs, pause, and it has run to the breakpoint. If I play again, it's on the next iteration, and so on. One thing is it remembers. If I restart, let's end that thing. I hope this now works. I haven't tested beforehand. Accept in, starting, run. You see my breakpoint is still there. So I have gone completely out of DDT. It stores these breakpoints from one session to another one. So if you have a debugging session and set a few breakpoints, you come back the next day, you will find that these are still there. Sometimes I find it annoying, sometimes it's nice. But that is how it is. You can always go in, so I need to pause here. It has run to the breakpoint. I can just, if I dislike that, I can just delete them here. Or I can disable that temporarily. Another thing on breakpoints is if I put the focus on process, and let's set a breakpoint on this line. So this breakpoint, since I had a focus on process 0, this breakpoint is now only for process 0. If I go for process 2, I can set a breakpoint on perhaps on here. You see this is grayed out. If I go for 0, it's this one. Process 1 only has that one. Let's take this guy out and run. So what has happened? I have run rank 0. It sits. Where does it sit? Don't know. I have to pause and it sits in the wait. It's waiting for data, which since I have only rank 0, which hasn't come. Restart the session. So, and if I just play, process 0 is in a breakpoint here. Process 2 is in a breakpoint over there. So I have set this breakpoint for process 0, this breakpoint for process 2, and these guys here, they are still playing. I cannot see where they are stuck right now. They're still playing, and if I pause this guy, you see it's stuck in the wait, and that is this is stuck in that wait. They're waiting for data. Any questions? Okay. How many cores to ask? 5. Let's take that down to 4. It seems I lost my DDT window. Did I hit the wrong? And there is the request, accepting a connection, run. So this is now a C code. we can step as before. And what that code does, it is an MPI implementation of large summation. Essentially, it's summing 1 over n squared, and that has been parallelized in a fashion that task 0 takes the first elements, then the next slot goes to task 1, and so on. If you just step here, it can. So you see again here these nice graphs. In summary, we are calculating 10,000 elements. We want to have the sum of 1 over n squared from 1 to 10,000. And if we now have a look, my start on rank 0 is 1 to 2,500, 2,501 to 5,000, and so on. As before, we can step together. So I is now 5,001 on rank 2. Next iteration, I is 2 on rank 0. So this works in. So I can go here in lockstep, and as before, I can do individual guys. We can now do a run to here. I can check that everyone is there. So every guy has finished their work. And then here we have a handcrafted implementation of a reduction operation. If rank is larger than 0, they send to rank number. There's a send operation of their own result to rank number 0, and rank number 1 just goes over all the tasks from 1 to world size -1 and collects the result. If I step here on process, if I step 0, that goes in here, and it waits for a result from rank number 1. If I go to, this hasn't come out of that. I had to focus on process when I did the run to here. So let's see, everyone is now on line 42, with the exception of rank number 0, which sits in the receive and waits for data. If I step number 2, it can go to the send. And since rank number 1 is not listening, it can't finish. If I go here, rank number 1, it has finished, and rank number 0 has come out. So you can see nicely how the MPI library is working, how it is coming out. Now he's asking rank number 3, and rank number 3 hasn't sent his data. So you can see these things, how the stuff is working. Any questions? Any comments? Restart session.
I do have one in the chat.
Yeah. What do you mean with, can you elaborate?
Yeah, let's suppose you have this project folder, and then for solving the issue, you need to add, let's say, a function, but outside the current file, like an external function. Can you add it, or do you need to do it everything inside the files that you have already loaded?
Okay, I have no example of a modularized project. Let me just start the next code and then I can elaborate on that. I'm not 100% sure I understand what your concern is, but I need to put that to off and I accept the connect. No, sorry, this was not what wrong version of the code. I wanted the Fortran version. No. That. So if your source code is scattered over multiple files, so for instance, here I have this is just one file. It has this one file listed. If it's multiple files, you see a long list of all the files you have here. And if you open like that, you get the methods included in the file. Is that what you asked about?
Yeah, let's suppose you want to add another file. Can you do that from
It's
here, from?
Not sure. Not sure. I've never tried. Normally it just by magic finds it. So if the source code is littered about 5 sources, then you find all 5 files here.
Okay, perfect. No problem. Thank you.
So what this is a parallel matrix routine. And what I wanted to show with that a few things. There's a line here. I have focus on group. And I do a run to here. So here's the matrix multiplication. And if I want to go into that, so let's step. And what has happened now? This is sometimes compilers, when doing a call, they insert code. So for instance, if you just have a look here, you have this call, it takes a few arrays, data structures. And so it has to check that you're not slicing. So it's a Fortran, in Fortran, if you pass an array, you could pass an array slice and then it needs to copy over. So the compiler, if you have arrays here as arguments, the compiler inserts code, and we are currently debugging the. You can just see it here. It comes out of libg Fortran, so it is it's associated with GC11 stage 3 object. This is not what we want to do. So a way around that is that you just, for instance, set a breakpoint here. At breakpoint for all. And then you just hit the play button. And then we are in here. And now we can debug inside this routine. So there are a few cases. We will see that in a minute also with OpenMP. OpenMP, if you start a parallel region, it inserts a lot of code. And typically what you do not want to do is debug the OpenMP library. Then this is a trick you have to remember. If there's a lot of code inserted by the compiler, you need to set a breakpoint, or alternatively, you can use a run to here to get to that point. I delete breakpoint for all. If we just restart session, I can go in here directly, matrix multiplication. I know I want to debug in here. So I just right click on here, run to here. And all the guys are here. If I know the problem sits inside the routine. Let's step out of this. We are back here. I want to show something else. I can go for this variable. And for instance, this is an array. I can use the array viewer. And I can visualize. And that is what you get here. If I know how the code works, you can quickly see a check for outliers in the array or. So this is it is a one-dimensional data structure, and if you check beforehand here, it has been initialized in a way that starting from 0 to a large value, incremental straightforward initialization, and you can check here that there are no outliers, that the thing behaves. So this is in particular for matrices. This is actually very, very helpful if you want to debug. If you know how the matrix is arranged, if you know how what the data should be like, you can check very quickly that there are no outliers. There is one other thing I want to show here. This is so-called watch point. It's something which I personally quite like. So here I just do it as a play. If I just have a right click and proc, the variable, I can add. No, come on. Why is that now not working? Oh yeah, here at the watch point. So I found it very useful once when somewhere in a larger project, data was suddenly modified in a fashion I was completely not expecting. So what you can set, if you have a variable which was modified and you don't know where and who and it was modified, you can put the watch point. So it's right out of the box, it is right only. So if the variable is changed, it will stop. Since this is here written only once, I go for edit and just change that to read and write. So now I have changed that watch point whenever nproc is accessed either as a read or write, the code will stop. In a real life situation, most of the time, this default of write is what you want. So if you have a storage location which has funny values and you do not know where this funny value was written, put a watch point on the data, and if you have a look here, it's implemented in hardware. It checks on this storage location. It doesn't check via the name. So if, for instance, you have overrun data structures or whatever, if that storage location is accessed, it doesn't check on the method how it is accessed. It checks on the location. So if you just have a run here, process 0 to 3, if you pause, you see it's written at MPI comp size. It modifies the number of processors. If I continue running, rank 0, and processors, if it's 0, so here that is a read access and it stops. Here it's on rank 0, and here it is on everyone. And this is normalized with the number of processors to work out how large a data structure. So this was just a demonstration of a watch point. As I said, in real life, most of the time what you want with a watch point is this, what's the default, edit, write only. Whenever the variable gets modified, the code will stop and tell you where it stopped, where the variable was modified, which routine modified the variable, and then you can think whether it should be or should not be like this. Okay, I would like to go into OpenMP, and yeah, this is not as nice anymore. But as far as I can see, it's the best shop in town. So years ago, I had contacts to a consultant from ARM, and I said, this is a bit clunky with OpenMP. And he said, yeah, it is a bit clunky, but that is how it is. So let's see. So here we have a script. Standard parts. I ask for 5 cores. I set OMP num threads from the Slurm CPUs per task. I do a DDT connect, and I give the name of the OpenMP executable. So let's finish this one here. And let's start this one. And if you set this OMP num threads, it figures that we want to run on 5 threads. So let's start. So right now, since we haven't started any threads, there's just a master thread here in the serial region. And we can just, it starts with the first statement. There is no MPI in it now, so you can debug from the very beginning. It starts in main. We can step. Here's a parallel region, and I will just step like that. It went over the parallel region. It doesn't go into. And that shows you a bit how OpenMP compilers work. What it does, if you do a parallel region, it packs everything which is in here, it packs it into a function and it gets called. The GDB, it doesn't really understand the OpenMP so well. So for GDB, it's just a function and it steps over. You see, since I had a parallel region here, it went over, and now we have the 5 threads running, the 5 threads we asked for. But since we are back in a master region, it is only the 0 is active and the rest is just sleeping here. Here was just a timing call, and then we have the next parallel region. And in here is the real work of the program. It sums over a triangular area, so it's an example for a load imbalance in an OpenMP code. And if I just hit here, go straight over, it just went over it. It has done all the magic, and now it's going to print the results. So now we have finished, and we can start over. Yes. So this is not so. If you want to debug an OpenMP code, we want to debug inside parallel regions. So let's go just here, do a run to here. Now, so based on what I explained beforehand, the compiler takes everything from OpenMP parallel until that ends, which is here, and puts it into a function. So what we have to do is we might want to step in. So let's see what happens if we do step in. Suddenly you have that problem again. If you just have a look here, libgomp, that is the GNU OpenMP library. The OpenMP library has inserted a lot of code which we don't want to debug. We want to debug our application. So we have to play the tricks again, which we had beforehand. The compiler between here and there, it inserts a lot of code which we do not want to debug. So if you do a run, just a run to here, Now I have our OpenMP threads. A few more things. If you have a look, this is an OpenMP loop construct. Here was originally an I, and this I is optimized out. It has created a private I. The loop variable is always private in a loop construct. For each thread, it has created a private variable, and I can step now here through the threads. This uses a static schedule of 5. So iteration 0 to 4 go on the first thread, thread number 0. This guy here, he gets iteration 5 to 9, and you see the I starts at at 5. Another comment, since this is a loop construct, if you have a look for this source line here, you will get statements that this line has been optimized out. It's not there anymore because OpenMP has to sort of to eat it. So now we can hit here step threads together. And we can have, for instance, a look of the J. The J is 0 all over the place. And we can step in here. If you want to run the threads together, you have to highlight process and click step together. Similar like MPI, you can run individual threads, and we can just progress this thread. And the other threads should be stuck where they were. Thread 0 is if I set breakpoints, it's for the individual thread which I have highlighted. If I want a breakpoint for everyone, I need to go here and set a breakpoint like this. And then it's a breakpoint for all threads. If I want to get out again, this is quite tricky. Let's just remove these breakpoints, otherwise they will irritate me. So I just deactivate those. If I want to get out, I can, for instance, set here a breakpoint for all in line 72 and hit play. Again, that is in order to get out of all the code which is involved with shutting down the parallel region. So important here is I think that should also work. I haven't tried that. Delete breakpoint for process 0. File. Restart session. I should be able to get out with a run to here. No, it hasn't recognized this. So I need to click here, run to here. I'm in the threaded region and can step these things together. And I can do a run to here. No, that doesn't seem to work. So, okay, if you want to get out, set a breakpoint after the end of the parallel region and do a run, do a play. As I said, OpenMP, it is a bit clunky. Okay, any questions on OpenMP? I want to get into Python now. So here I have DDT connect. Tell it that I want to use OpenMPI. I have the MPI run. I have the Python 3. I have this alinea string. And then I have the Python script which I want to debug. I need to terminate this. I accept. And I go to run. And I'm inside here. If I were to step, this is you would get similar problems as before you are debugging the importing. So the recommendation here is that you just go here and run to here, and then everyone is here. You can see a standard thing in Python. Python, you don't declare stuff before you use it. Currently, there are no local variables. If I step, then mycom appeared, and it's a communicator. I can step. Size appears, size is 5. I have a rank. I get again this little diagram showing the values, and I can print. With this version of Python and that Python library, it seems to have located the Python script okay. I have worked with other versions, older versions, and it hasn't. If it has the wrong stack, you have to go. So for instance, here it's now we are into something out of linear. You have to locate your Python script inside the stack. You have to check that. I have one last thing, which is again a Python. So let's just stop this. So this is again a code of a message around the ring. And it starts off inside the import statement. So I do a run to here. So the first line. So we create a list of length 100 and that gets exchanged. Please note that this is a buggy example. Don't do it like this. So what I've shown here, this is a severe bug. And I just want to show how it does it. So if I create a list of 100 elements, going over, working out my neighbor. And then here, for instance, we create the list. And if you have a look, it says append is a Python list of length 100. I can open and I can see everyone is set to 0. On rank 2, everyone is set to 2000. And rank 4, everyone is set to 4000. So here you can see the contents of that list. You have a second list. And if we now hit run, the program runs OK and prints the result. Let's just modify that thing. No. I put the list length to 10,000. Where's my DDT? Has that vanished? Oh, that's bad. No, should be running somewhere. It's not here. Where has that disappeared? No, no. Jobs has finished. Submit again. It's a window. Accept in. Run. And if I hit run, the code suddenly freezes. So we have here, we have the vector length of 10,000. The elements are now 10,000. And what we have produced is a deadlock. If I have a look, you see all the tasks are in here in the send. So they send a large array of data or a large list of data. they send a large list of data, and the list is so large that the send has resorted to a rendezvous type protocol, and everyone is trying to send data to the up neighbor, and the up neighbor is also trying to send to their up neighbor, and the code has deadlocked. And nobody issues receive that everything can be released. So in order to fix that situation, you have to use a non-blocking send, send operation here, such that the control comes back. I send, then you do the receives, and then you do the waits. So with the debugger, we have quickly found the position where the code deadlocks. Let's, since time is running short, we are typical signatures of memory problems, writing in memory locations where you shouldn't, are things like segmentation faults or code behavior changes when editing. Example, for instance, printf debugging. I have seen that putting a print statement, the code behavior changes, changing compiler optimization flags. So to activate memory debugging in DDT, you replace the malloc library with Linearus dmalloc library, debug malloc. It comes in 4 versions: C and Fortran no threads, C and Fortran with threads, C++ without threads, and C++ with threads. The current version, I think it creeps out of the MPI library, is that you have to give threads because the MPI libraries are threaded. So to select memory debugging inside this window, which we had before, you click here on memory debugging. And then you go into details and you get an interface like that. It can check a lot of things around the heap. So as a standard recommendation, when I use memory debugging, I put that on balance. That is, the slowdown is not so bad and it does a lot of the checking. And then we can, then another thing what we can do is that we can have guard pages. So to start off is you hit here to preload the memory debugging library. That is if you have dynamic linking. If you have static linking, you have to relink your application. And then typically I recommend here if it's C and Fortran with threads. If it's C++, it's C++ with threads. I said that before, the case we had 10 years ago, you had to do static linking, so you had to do stuff like that. I haven't really tried on Dardel whether this supports now dynamic linking or static linking. What I wanted to show is guard pages or electric fences. It's a very common problem if you have a memory allocation and then you overrun, you write behind the end of an array or beforehand. And to put guard pages, it's in my view a very powerful feature to check. So if you have a memory allocation, an array structure or something like that, you put it one or more pages behind. And that is the dmalloc library of the debugger does that for you. And then it checks if there are accesses into the guard page. It knows that you have overrun your array. You have to choose whether to put your guard pages after the memory allocation or before the memory allocation. So you can check for overrun accesses or underrun accesses, but these are separate runs you can't do in a single shot. And you have to beware if you have here if you have your guard pages, your memory runs out more quickly. So if you live at the edge of your memory, you might have a problem with these guard pages or electric fences. So to activate that, you click here at guard pages. You can select how many guard pages you want. So here it's selected one and it's placed after. You can, as I said, you can alternatively choose to have it beforehand in the separate run to check for underrun array data structures. And when it finds something, you get something like that. And in my experience, it's a killer feature. So let's go back to, so I have here an application which has memory issues. I just do a DDT connect and I use an OpenMPI as beforehand. I have 4 cores. And so let's run that. Yeah. Okay, it comes. So you want memory debugging? I had 4 cores, so I need to change that to 4. I want memory debugging. I go on details, and here I can preload memory debugging library. It's Fortran with threads. I have a balance. I have add a guard page 1 after the thing. And if I run, and here I can just run, and it finds it. So I can pause and check. If I have a look at results, so this is a Fortran example. It is a data structure of, no, it's allocated. Okay, it goes away if I, no, vendor. It's declared as real kind 8 allocatable and it is allocated 4096 elements. And if I have a look at K is 4096 plus 1 is 4097. So here it tries to access one element after the end of the data structure, and it directly found that. So now you have to work how to fix that. I have shown how to start the GUI. If you run out of the batch script, you start the GUI on the front end, and then you put the DDT connect in your batch script. Alternative, you can use an interactive session. I have demonstrated how to run it. I have shown a few features, and then I showed you the memory debugging feature, which has saved me a lot of time in the past years. If I suspect the memory problem, I just put guard pages behind and typically finds it quite quickly. Alternative, I never seen a case so far where I had underrun data structures, but if it doesn't find it in overrun, I would try an underrun. Okay, at the time I started this presentation, I had help from Johan Guau and Patrick Wohlschlegel, which worked back then at ARM, and Thor Wickfeld, who was then at KTH. He has now moved on to ENCCS. Any comments, any questions left?
Yeah, thank you for a very useful and detailed presentation. Could we get your slides?
Yeah, I typically do that. I share the slides.
Yeah, and I'm also wondering, would it be okay if we shared it internally?
Sure,
Okay, thank you.
sure.